which is not correct because I can show that elements of that free group or elements of that group can be written down as beta to the k, alpha to the j for some k and j. You can move them past each other so that you only have to deal with those. But then in order for this to be isomorphic to Z2, you can just check, oh, well, let me take an arbitrary element G, square it. It should be equal to the identity, but that only works if G was already equal to the identity by just checking cases. So I'm not.
Did you just say that you get alpha beta inverse as your relator?
Yes.
Somehow you accidentally found the fundamental group of the torus.
No. I said alpha, beta, then beta inverse, right? The
Yes.
other one is the torus, right, is alpha, beta, alpha inverse, beta inverse.
Unless I'm remembering what I did wrong with
Because the
daily and
torus
office hours.
is the free abelian group on two generators.
Right. Oh yes, yeah, okay. I might be forgetting an inverse.
Yeah, because that relationship is
reasonable.
going to be alpha beta equals beta alpha, which works out to alpha beta inverse beta inverse. So like,
Yeah.
I guess I'm just wondering like whether anyone like it jumps out to anyone what the hell happened, and why specifically picking the base point to be at the corner rather than removing that disk and doing some work to show that it's the Mobius band doesn't work. Or maybe if I did it correctly, I would have gotten the Mobius band and just putting it at the corner obfuscated that.
Jacob, what did you all do yesterday? I had to give my talk, so did you do the disk Mobius solution, or did y'all try something else?
Let's see. Did we talk about this problem yesterday, Catherine? I don't remember.
No, I think we were talking about, which one? I guess simpler one, like S2 or something.
Yeah, we were talking about like breaking down, like just doing some basic Cypher-Van Kamp theorems for like the torus and like the sphere and things like that. Yeah, and also Anthony asked a question about one of the exercises to know, which ended up being wrong, and I had to correct it. So if you've tried part 2 of question 6, or 6A, as I guess I'll call it for the point set topology question, 6A part 2, the version that I had was much hard. Hard as in the true math hard is not doable, I don't think. So it's been fixed to the correct version, to the version that actually appeared on a qualifying exam. So I thought that the way that I've stated it was equivalent, but it wasn't. Yeah, and that's what we did during office hours yesterday. I don't record office hours, so if you're watching this in the future, then come to office hours. Unless it's like super far in the future, in which case this will be lost to the sands of time.
Shannon, I think you asked me for notes, so I can send you. I think Jacob made a really nice list of like basic rules to know about like fundamental group stuff. So just remind me, I'll send it to you.
Yeah, or okay, reminding. Yeah.
Yeah, and to talk about Raoul's question with this Cypher-Van Kampen theorem for the fundamental group of RP2. Yeah, the hard part is definitely doing the amalgamation part of the problem, right? Viewing how the generator for the annulus has degree 2 in the Mobius band. All right, well, it doesn't have degree 2. That's wrong. It becomes a relation, right? But no, I do not want the Zoom whiteboard. Why did I do that? Yeah, so I don't know if I'm going to be able to explain this in a way that's better than the article that I posted in the chat, which, because I started the recording late, there's an article from Math 3 MA that proves this with a nice video and some much better pictures than the pictures that I draw. So really, you should just read this article. It's very short, but yeah. So here we have an annulus. And Raul, where do you want the base point? Okay. So if I identify two antipodal points, or antipodal points, I guess that's how like real mathematicians would say that word. Right, I can turn this into a Mobius strip by identifying these two edges like so. Right, so you can imagine that if I glue in this internal disk, then I get the, right, so this is a annulus, this is a Mobius strip. And here, if I don't cut out a disk from the inside, if I just have this like this, then this is RP2. Are there any questions about why this thing on the right is a Mobius strip?
Yeah, it's like messy in my head. So what's the clean way of saying the reason it is?
Yeah, so the way that I do this is that I cut out these edges here, and then I do a gluing and pasting, right? Do some gluing and pasting to put the black marked edge in the middle, and you'll get like blue, blue, red, red, in the same, sorry, the opposite orientations. Yeah, you'll get something that looks like this. It might not be exactly this, right? Like it might be like the black arrow is pointing the other way or something, but you'll get something where like you cut apart the blue and red strips, and then you like rearrange this to paste the black strips together, and then you get the thing which looks more like the Mobius band. And I only speak about this confidently because I did this last night on my stretch paper. So. Okay, cool. Okay, so if I have, say, like this left corner as the generator for my annulus, then I have here a loop, which I'll call gamma. So that way my annulus, the fundamental group of my annulus, is generated by gamma. I'll stick with green since we're used blue and red in this picture. And then my generator for my Mobius strip is beta, like this. And if I follow the gluing and pasting that I did here, I'm going from, let's see, this corner, I guess I could write this as this corner to this corner as beta. No, those two corners don't get identified. Those two antipodal points do get identified. Oh, that's because I marked this, the arrows here incorrectly. Yeah. So I need to switch the colors on my arrows here. This is supposed to be the blue one. This is supposed to be the blue one. This is supposed to be the red one. This is supposed to be the red one. Okay. Cool. So lifting my beta, I am going from here to here for beta, or like my generator is just the center beta here. So when viewed here, it's clear that beta goes around the Mobius band once, right? And the Mobius band is a deformation, or deformation retracts onto the circle, right? Just by like a straight line collapsing onto the center circle of the Mobius band. And so, yeah, then when I include, right, so I have like I1, which takes, say, pi1 of the disk. No, not the disk, pi1 of the annulus to pi1 of the disk. And this is just the trivial map, because pi1 of the disk is trivial. And I have I2, which sends pi1 of the annulus to pi1 of the Mobius band. And I can determine what a group homomorphism does by just looking at its generators. So I just have to ask what happens, right, to the generator for the annulus, right? Well, what I do for the annulus is I just take this curve for the annulus and I just include it into the Mobius band. Right? So this entire thing is gamma. And I can put another copy of beta in my space here, right? This is also beta. Yeah, and so the observation is supposed to be that gamma is equivalent to 2 of these beta maps. I don't know if this is more or less compelling than the Math 3 MA article. So I don't know if this actually addresses Raoul's statement, but one way to do this is to just slowly move this point here to that base point in order to see the equivalence.
Which point, Jacob?
Good question.
Let's see what color.
Yeah, let's take this point on gamma and move it to the black point.
Are you saying the green point? Oh, over there. Okay, sorry.
Yeah. Yeah, is this going to erase the entire curve? Yeah, it's going to erase the entire curve, but that's fine. Yeah, so instead of viewing gamma as going around once through like the middle, I can deform gamma so that way it hits this point and then goes back to the original base point, right? Like this. And then it might be more clear that since, and I guess that I should make it more clear, that this top copy of beta is just the single curve, right? The single curve goes from this bottom corner to this, or the left point to the right point. And then another copy of beta goes from the right point to the left point, right? Right, because I'm just doing this single beta twice, right? One of these betas goes from here to here, and then the second copy of beta I'm drawing from here to here. Or another way to see this, if I like try to do this in like movie picture mode, and I'll draw a new diagram here. So this will be the same. So here I have one copy of beta, which I'm going to leave down here. And then I'm just going to draw another copy of beta, and we'll draw the second copy of beta in light green. And what I'm going to do, if I identify these edges, if I slowly move the second copy of beta closer and closer to the top, right? So I'm going to move it up, and then I'm going to move it up even closer. When it is on the top edge, it is both here, and because opposite edges are identified, right? It's both of these, and then it moves across and it switches orientation, right? And then I get my copy of beta, which is on the other side down here, right? So if I think about moving the dark green curve up this way, I can move it across the black edge by switching its orientation this way, right? So I get one copy of beta, which goes clockwise around the top, and another copy of beta, which goes clockwise around the bottom, right? So those are both copies of the same curve beta.
I think I have a question. So I guess just to make sure, like when you're using the Cypher Grand Canton and you like, it's like literally each element from like each element gets identified with each element in the image. Like it's just like this element to element correspondence.
Yeah, it's the map. Okay, so it's not an element to element correspondence in groups, right? What it does is it just takes your curve in your subset and just includes that curve into the bigger space, right? But it could be that you take a non-homotopic. So for example, I can include the plane minus a ball. This certainly includes into the plane. And then that inclusion induces a group homomorphism, right? From R2 minus the ball of radius 1 at 0 to pi 1 of R2. But this group homomorphism is not injective, right? Because this is trivial and this is not trivial, right?
I guess like the image of an element in like that left-hand group, like it's just going to be like I of I don't know.
Yeah, so if we call this I star and we call the original map I, which is how
Yeah.
we normally do this, yeah, then I star of the homotopy class of a path is just equal to the homotopy class of I composed with the path. Yeah, so you take your path and you just include, yeah, so, right, so just to draw a nice picture, right, here's my gamma, and then I can include this into the plane without that open set, right, and then I just get gamma again, right, which is also I composed with gamma.
Yeah, so when you go to Seifert Van Kampen, it says like either way you move around the diagram, you should end up at the same place in the image. Does that make sense?
Yeah, so this diagram is supposed to be a commutative diagram, right, if I remember my
Okay.
diagram correctly.
Like, I know it's a silly question, but like that's what Seifert Van Kampen is giving you, is that either way you move around, you get to the same place. Like that's how you get those relations.
Yeah, so the way that I think about these relations is that, so when I have U intersect V, this includes one direction into U, and it includes one direction into V, right? And then these two sets both include into the original space X, right? And then there's like other things that you do in order to make the push out happen, right? Like I said, I normally don't think about the diagram version of the Seifert Van Kampen theorem. But what's happening is that, okay, I'm going to write U as a group with a list of generators.
I guess
Then
my
I'm-
other question, so they're always going to give us like groups where the generators aren't, like there aren't like infinitely many of them or something like that.
Yeah, so in topology, we normally work with finitely generated groups. Yeah.
So it'll be like the problems that they would ask us to calculate the fundamental group
Yeah,
for
certainly
is-
on the qual, you would certainly be given, right, like it's only a couple of generators, yeah.
Okay, so there might
But
be like oh, go ahead.
Yeah, but the idea is that like if I write V, right, this is gonna be like generated by some collection of gammas, right? Followed by some relations on V, right? And the fundamental group of U, right? This is gonna be generated by, let's call them Greek letter, let's call them deltas, delta 1 up to like delta n. And I'm just gonna pretend like that these only have, you know, like a finite number of generators, and then there's gonna be relations on U, right? But because U intersect V is connected in a locally path connected space, this is path connected, right? So some elements of this group, right, they're going to exist some G's in this group, which are represented in here, and they're going to exist some H's in this group, which are also are going to be represented in here. And you want to be able to say that those group elements are the same. Right? And that's exactly what this I1 of G inverse I2 of G thing in the Seifert-Van Kampen theorem is saying. Right? It's saying if a group element can be represented, if a group element in U and a group element in V can both be represented in the intersection, then we want to view these as the same, right? Here they are different group elements because they're generated by different things, right? But in X, we want to view those as the same group element. And so that's what this modding out by this entire thing is doing. It's just letting us view the loops which live inside the intersection as the same element. So from like a pictorial point of view, right, if you have like, here's your U and here's your V, right? It could be that like one of my generators for U, like this is my base point, right? This is delta 1. And here I have like gamma 2. But the way that I drew this in the picture is supposed to be indicative of the fact that delta 1 is supposed to be equal to gamma 2 in the big space X, right? So you need to be able to say that these two are equal in the big space X, and the way that we formally do that is by this relationship, right? We add this as a relation, right? Which says that the image of gamma 1 inverse times the image of gamma 2 in X is a relation, i.e. these two things are equal. Because saying that this is a relation is the same thing as saying that I1 G inverse I2 G is equal to 1, which is the same thing as multiplying both sides. I2 G equals I1 G, right? So that's what we mean when we're adding this relation. We're saying that these two things are going to be equal, right? And we're just formalizing that.
So like essentially to create these relations, you like, I don't know why I can't say this correctly, but like equate generators like through, well, you do that.
Yeah, so it might not be equating generators. Like for example, in this example, right, I took a generator from here and I got a non-generator. But yeah, you equate group elements which can be represented in the intersection, right? Oh, you already re-added your solution to the Mock Qual document. I was about to re-add the solution that you sent me because it's better than mine.
I mean, it's still kind of rough, right? Like you have to worry. I was gonna like fix it, but then like my computer crashed and I had to reboot it. So I'd say it's good enough, right? Like I'm not like gonna worry about it.
Oh no, as you know, I had questions being like, wait a minute, why are these things true? Especially, I don't know. I think it might be useful for other people reading this if you at least write a sentence explaining
Yeah.
what
I mean,
your subtraction
I can,
is.
yeah,
Yes.
I can fix that later. I just,
Okay.
for
Cool.
whatever reason, Zoom likes to kill my computer if I try doing more than just Zoom on it.
But
Yeah,
I want to let you know
my
that I did reopen this tech file that you sent me because I was going to re-add your solution after you pointed out that mine was fatally flawed, much more fatally flawed than prior solutions.
Jacob, can I ask you about number 4? Or are we done with this one? Are we still on this one?
I mean, that depends. Are there any other questions on this one?
Oh, okay, yeah. Well,
But yeah,
I know
I'm-
you Yeah, I know you all did a basic one in office hours that like, would be nice to understand the overall, like in a very linear way. What it, you take a space, what is Seaport Van Campen trying to do?
Yes, so yeah, I admit that I did not go through all of the steps towards this one in a lot of detail.
Right.
But the article that I linked in the Zoom chat, I think,
Sure.
does go through in very nice detail. So I'm gonna
Mhm.
outsource the work I'm supposed to be doing, just a different resource.
Right.
Yeah, so you had a question about number 4 on the mock
Yeah,
call?
number 4. So, like Catherine and I met up and did some fun stuff. So on the or did you all go over this one in office hours? I don't see that one, right, Catherine? The retract. We had a question about, so it looks like the retract is only a single-sided, it satisfies a single-sided identity condition, right? Not on both sides, it's just
That's right.
ROG, it's not the identity, okay. So with this inducing, sometimes that word gets a little fuzzy, right? So I see that Raoul has this and he says by functoriality of pi 1. So are we actually meaning categorical sense or something like that? We had a question about how that induces. And then we also had a question about how you actually visualize S1, direct product with the singleton 1. And then how that actually, what that actually means. In
Yeah,
terms
so by
of,
functoriality, I mean, I don't remember whether we covered in class that pi 1 is indeed a functor, but in particular, I mean that when you compose two functions and then pass to you do you do the starring, right? It's the induced map on fundamental groups. This splits as the composition of the induced maps on the respective fundamental groups. So that's literally that line that I have there.
Mhm.
And then S1 direct product with 1 in my mind is just like a formalism so that it can then fit inside to the torus. And then you just get the wedge of 2 circles.
Okay, right. And so fundamental group of the wedge is what?
Free on 2 generators.
Okay.
Yeah, so
I was just lazy and I just said, oh, well, abelian, done.
yeah, so S1 cross S1, this is the torus that looks like this, right?
Yeah.
And so what we're doing is we're just going to identify, say, this point as the point 1 cross 1, right? If I'm viewing S1 as a subset of C, right, then I can just look at the point 1, right? That's what we're doing here. Right? So I'm thinking the rightmost point is the point 1, and up here's the point I. Okay, you all get this. Then if I look at S1 cross 1, all that I'm doing is I'm deciding which of these circles is going to be my first coordinate. And then when I look at 1 cross S1, then that's just going to go the other way around the torus.
Mhm.
And so this means that the union of these two, right, if I take the union, it's going to look like the red circle, okay, wedged with the blue circle, because that's exactly what I ended up drawing. Wedge point. And then as Raoul said, this fundamental group is exactly the free group on 2 generators. Yeah, and this is just the explicit functoriality of the diagram that Raoul was saying. If F is the composition of 2 functions G and H, then taking the pi 1, the induced map for pi 1 of F is the composition of the induced map for the composition. Yeah. So nothing on this page that rule did not already say, just some pictures to accompany.
Yeah, because they didn't, I don't think anyone talked about like a category, the category of loops or category of anything, right? But we can just use that.
I think we did, I don't know whether we did it in the full generality. I think we explicitly showed in the end of part A, possibly the
Mhm.
beginning of part B, that, you know, this composition works, right? Like, or when you take a composition, hit it with with pi1, this is the
Mhm.
same as taking maps, hit them with pi1 and compose them.
Mm.
But we may have talked about it as like, oh, this is like the functoriality, or that might have been in a different class. I'm not sure where we actually explicitly said pi1 is a functor.
Cool.
Yeah, you can do this just using like the definition of a homotopy between paths and just being like, well, a normal homotopy between paths has domain like 0, 1 cross 0, 1, right? Where the first one is the domain of your path and the second one is the thing which interpolates. And if you want to break up this homotopy between G and H, you just break up the interpolation from 0 to 1 to 0 to 1/2, then from 1/2 to 1, and then you break up the map in the middle from G. And yeah, there's like a way to go through this carefully where you use the definition of what it means to like concatenate paths and, you know, what it means to like put this homology on like the composition of two functions and show that like you can break that homology down into a homology on the first function followed by homology on the second function, things like that. But yeah, so knowing Schultz, he probably just said, yeah, whenever you know, induce the map, it works, right? And then you moved on.
I think we actually explicitly did at the very end of part A. I think we actually explicitly showed that, you know, the starring works, but I could be wrong.
Yeah, that does sound like something that Fiduci would do. So
I think we did. It's also like in Moncrief's, right? Sorry, I
I think it's in
it's also
Hatcher.
it's in Moncrief's before Covery Sakes. It's probably in Hatcher too.
yeah. Yeah, I'll be the first one to admit I don't think I've ever opened Hatcher.
Why not? Hatcher is a beautiful text.
I can't disagree because I haven't spent enough time looking at it. Okay, I have opened it up a couple of times, but I've never like, I don't know. Schultz has his like list of notes that he uses, which follows his course very well, and they are very well typed. So that was the textbook that I used for part B.
I found following Schultz's stuff very difficult, so I used Hatcher plus some guy, what's his name, Pierre Albin. He does videos from Hatcher.
Yeah, I'm not saying that following Schultz's lectures was the easy part. I'm just saying that like reading his notes, I was just like, okay, these notes are actually quicker. All right, any other questions about mock qual number 4? Or mock qual 1 question number 4. Right. We don't have 4 mock quals yet, right? We haven't missed. Okay. One problem that I think is worth talking about would be question 8. Just because I would like to present a different solution. Roll's solution is very nice. It uses the chain rule, and Fred really likes the chain rule, so he'll be very happy to see that. But there's a way to do this problem where you only need one fact about differential topology, and then the rest of it is a point set topology argument. So I could change one word of this problem and just stick it in part A instead of sticking it in part C. So the fact that you need is that every submersion is an open map. And then once you have this fact, the rest of the argument is quite nice. So outline 1, f of m is open, since f is an open map. F of m is compact, because f is continuous, right? So this means that f of m is closed, since R, did I use K? K is Hausdorff, right? A compact subset of Hausdorff space is closed. Right, this is one of the exercises to know, or if it's not, it should be. Right, then for RK connected, and FM Klopen, this implies that FM is equal to all of RK, or FM is the empty set, right? Because, right, it being closed and open means that it's a component, right? So RK only has one component. So either it's all of RK or it's the empty set. And then 5, FM is not equal to the empty set, right? Because it's, yeah,
Because
it's a
it's
smooth
not.
compact, right? Because M is not empty, right? And the function has to send those points somewhere, right? And FM is not equal to RK because RK is not compact.
So Jacob,
Yep.
I had a concern about this after I did my proof, and it isn't resolved here. K bigger than or equal to 0, R to the 0 is a singleton, no? So in this proof, right, well, R to the 0 would be compact. And in mine, what the hell is the tangent space to R, 0?
Yeah. Yeah, because R0 is compact, and so we don't get a contradiction here. But is
And
there?
in mine, the only thing that I can think to say is the tangent space to R0 is R0 itself by following the same formula for
Right.
RK. And then mine breaks on 0 as well.
Yeah. It's possible that this is a typo on my part and it's supposed to be k is greater than 1, but I don't think so. I think that I pulled this from, did he put this on this year's exam or did I pull this from like last year's
He
exam?
did put it on this year's exam, and or he at least had it. I think he put it on this year's exam. And like I wrote this problem up for him at one point, and he didn't see any issues. So unless like maybe that was genuinely a typo.
Yeah, so I know that he had this problem on my exam. And this was the solution that I put on my exam, and I got full credit for this. So this is at least one of the solutions that he is thinking of for this problem. But yeah, it feels like that there is a submersion of k equals 0, that the constant map is a submersion if your manifold is a singleton. Okay.
I mean, not even any non-empty manifold. There's exactly one map. It's the constant map.
No, right, you're saying for any domain, like I can change the domain as long as the
Yeah.
codomain is a singleton.
Yeah.
Yeah, okay,
Right.
yeah.
R
Sorry,
to the
sorry.
0 is a singleton, right? It's
Yeah, that's what I was saying. As long as the codomain is a singleton.
yeah. Okay.
Then this
got it.
always worked. So when you said, wait, as long as it's any map, I was like, what? Whoa, I could come up with tons of constant maps which aren't submersions if the codomain is not a singleton. Yeah, include a singleton into R, right? Yeah, so we'll just put k greater than or equal to 1 here. Yeah, I can go to like the old exam and see if it was k greater than or equal to 1 on the old exam or something. This is a typo on my part. So I accidentally replaced a greater than with greater than or equal to. So here's the original final, and you can see here that the k equals 0 case is in fact excluded. So let's go and So it is corrected on the solution file, and I will go back and correct it on the other files after our meeting. Yes, thanks for pointing out that I made a typo. But yeah. So I know that the solution file does not have a rules solution under question 2, but did anybody do question 2?
I did. And
Yeah, me too.
Yeah, anyone who did it feel comfortable sharing their solution?
yeah, it's not very elegant, but I think it works.
Okay.
So
Well, okay, but real quick, were there any remaining questions or comments or concerns about number 8 before we move on to a different problem? Okay, great. Go ahead, Zachary.
okay, so show F's a quotient map, we want to show a set U is open in Y if and only if its pre-image is open in X. And we immediately get that if U is open in Y, its pre-image is open in X just because we're told the map is continuous. So now we need to start with a set U and Y and the knowledge that the pre-image is open and try and show that U is open. And so for that, if F inverse of U is open, then its complement is closed in the compact metric space. So its complement is compact.
Yeah, I'm gonna define this set to be equal to V, okay?
Mm-hmm. Yeah, so V is closed in a compact space. So V is compact. We know F is onto, so Y is equal to the image of a compact space X. So Y is also compact.
Okay,
Although hang on, we don't actually, I don't know if I needed that step yet. But we know that the compact image of the compact C is compact in a Hausdorff space, so it's closed.
okay.
And then I just had the complement of F of C, it has to be open, and then with just some like double inclusion arguments, just following through what it means, I got that the complement of F of C is U. And that just like, I think all I needed from here on out was the knowledge that F is onto. Yep.
Yep.
Just to check, for problems like this one and problem 3, is the claim that it's metric just so that we have like at least T2?
So the reason that metric is put on these so normally when you see a homework problem, you're given exactly the properties that you need in order to do whatever the problem is. For the qual, at least the reason that I could think of, like I don't write the qual, but for me, the reason that they give you metric is because metric has a bunch of properties and they want you to figure out which properties you need to do the problem, right? Because if they had given you this problem saying, let X be a compact space and let Y be a Hausdorff space, this problem becomes a lot easier because at every step you use the only property that you have on the space, right?
Yeah, I feel that because I started this problem trying to do something with uniform continuity because like continuous uncompact is uniform continuous, and I thought that might be the key there somewhere. And it turned out to not be a fruitful path to go down.
Yeah, exactly, right? Like they're testing you to see like, okay, we've talked about like a lot of properties, which properties should you be using, you know, like in order to figure out how to do these kinds of problems. Yeah, and then there are some people that get stuck trying to like use like metric balls to solve this problem, and you know, like trying to do things like, you know, well, a compact set is like a, right, you know, like a closed and bounded set, and trying to like use like these types of properties to like show, yeah. Yeah, so yeah, so one of the reasons that I included this in Mock Qual 1 is because there are several statements that are very similar to this, one of which is a fact, which I don't know if I put it in exercise to know. I probably should have, right? As I'm thinking more about these problems, I keep thinking of more problems to add. But there's this theorem which is stated in part A, which is actually used all the time, right? Which is that if f from x to y is a continuous bijection with compact x and t to y, then f is a homeomorphism. Right? And the proof of this is remarkably similar to what we just did. Right? Right? Showing that the inverse function is continuous is the same as showing that the original function is an open map, because the map is a bijection, which is the same as showing that the original map is a closed map, right? Well, this is a closed map for exactly the argument that we just did, right? A closed subset of a compact space is compact, the image of a compact set is compact, and then a compact subset, and then a compact set in T2 space is closed. Therefore, the image of a closed set is closed, right? So the proof of this is remarkably similar, but this is a very useful thing to know. And there are a couple of problems that Fred likes to ask where, you know, you stare at it and go, oh, wait, by this fact, this is just a homeomorphism, but then you can work on like trying to build it up to something that's smooth. Right? But there are a couple of problems that all follow this like same line of reasoning of like taking the complement to get something close and then like using nice properties of closed sets to like do that. Okay. So it looks like we just about have 10 minutes here.
Jacob, can I ask you one question about number 6? So
Sure.
When Catherine and I were doing like looking through like Hatcher just about Mayer via Torus, remember we used Mayer via Torus for that other problem, to get like the initial step for the homology of SQ, he always uses the reduced homology groups with the tilde. So can I ask you what's up with the using the reduced? Because we sort of said he's got some kind of, I don't know, corollary that the reduced homology of this is like the regular homology for S, you know, N. And then we used that and then just kept going down to get pretty much what Raoul has here. So just a question about why is anyone using reduced homology groups as opposed to the other one? Like if that just has to do with the chain complex. And then how do you actually get, what's a nice way of saying, you know, is it if the homology groups are not homeomorphic, if the homology groups are not isomorphic, then you don't have a, you know, like a homotopy? Like where's the chain between homeomorphic, homotopy, and that's what we were trying to figure out at the end.
Yeah, okay. So if I recall, and I don't do homotopy theory or homology theory, so this might be incorrect. The reduced homology of a group is the homology mod Z. So you just remove one copy of Z from every homology. And the reason that people do this is because they go, well, H0 of any connected space is always Z, right? And in some sense, this like extra, the fact that you're just in a connected space just like lives throughout your homology in like all of your homology bits. So if you mod out by Z at every step, you simplify a lot of the homology and you still get something which is a homotopy invariant.
Yeah, my original actually used, I just assumed reduced homologies actually, and Jacob, you corrected it to, since we aren't actually supposed to be using reduced homologies.
Oh, did I correct it?
Yeah, I had that H2 S2 O plus H0 S2 is isomorphic to Z, because I just said, oh, H0 is always nothing, unless you know,
Right.
it's and you're one dimensional, unless you're a 0-dimensional set.
Mhm.
Right. Yeah. Well, I mean, then like the homology for the sphere is just 0 for everything, right? Because it's Z in 2 places, but you mod out by Z everywhere, and then you just get nothing,
No,
right?
don't you, in the reduced homology, isn't it you just extract the 0, right? So I don't
Oh,
think
is it just from the 0th homology? Okay.
yeah,
okay.
so it's not, it's the reduced homology isn't modding out by Z everywhere. It's taking, it's you take the 0, which is always going to be Z, and you sort of extract it out. It's always going to be at least Z, right? So you just
Right.
extract it out. And you extend your complex by 1 position, essentially.
Okay. For me, it's harder to see why that's still an exact sequence, but maybe
I don't think it is
reduced homology an
exact. I think that's
sequence.
the
Okay.
thing.
Okay.
It fails
then-
exactness at that point, but you do
Sure.
it so that life is easier.
Yeah.
I don't know. I wasn't totally clear on why, but it definitely, I'm pretty sure, because otherwise there'd be no point in doing a reduced homology that says that, you know, Sn is always 0 in all the homologies, because that's not useful.
Right. Yeah. I don't know. Maybe Schultz was faster this year. I don't remember him talking about reduced homology in part B. I only remember him talking about reduced homology in the algebraic topology elective. So, but maybe he did reach reduced homology this year.
I mean, no, I didn't. I did most of it
Okay.
by looking at Hatcher.
Okay.
By Hatcher.
Um,
Yeah, because that's what we're confused, because reduced homology of H, like the reduced homology group HI of Sn is 0 for I not equal to n. So just like Rel is saying, like on the, you have H2 S2, which is obviously Z, but H0 S2 reduced homology is 0, not Z.
Yeah. So
Yeah. So mine
this is-
originally said H0 of S2 is the trivial
0.
group, but
Right.
then Jacob corrected it to use because we were only told to use singular homology, not reduced.
That's what it says on the first line. Homology invariance in a singular homology theory.
Ah,
Right. So, and we computed what the singular homology was for S2 in meeting 4. Was that the homology day from week 2?
oh.
I think was meeting 4. Yeah. So
Which
we
is
did
Z.
this, and that's considered, yeah, it's Z twice, right? Once for the 0th, once for the n or qth.
Right. Okay. So when you do have this difference, how do we say at the end? It's like you have, you know, H2.
Oh, so
Yes.
that, yeah, we proved.
Yeah.
Sorry, Jacob. I keep interrupting you.
No, what?
It's okay. Yeah, so okay, right. So how does this, okay, so maybe I should write if X and Y are homeomorphic, then there exists a function F from X to Y and a function G from Y to X, such that they're both continuous, and F compose G is the identity on X, and G compose F is the identity on Y. And we compare this with, or maybe I shouldn't put an if here because this is just a definition, right? X and Y are homotopic. And I'm going to do something cheeky, which is going to make it hard for you to write notes for, but it's going to make it easy for me to do. I'm going to copy, and I'm just going to add homotopy brackets. Right. And so the reason that I do this is to show that, hey, listing these two definitions in this way is a proof, which shows that being homeomorphic is a strictly stronger condition than being homotopic. Okay? Any two spaces which are homeomorphic are homotopic, but not vice versa, right? There exist homotopic spaces which are homeomorphic, right? Then there's a fact here, right, which says that, and I know that one way of this is true, right? If X and Y are homotopic, then HNX equals HNY for all n. And in fact, I also think that you get and the maps dn are equal as well, right? You get like an exact equivalence of, in fact, there's a, okay, I should be more specific than that. I should just say H star X is isomorphic to H star Y. So this is one of the subtleties which is often frustrating if you just listen to Schultz. When he writes H star X, that means the entire homology chain, which includes the maps between them. So this object here is the entire chain HNX dn hn minus 1x, right? Like that's what he means when he puts the star there. He means the entire infinite chain with repeated boundary maps throughout the entire thing. So when he says that this chain is the same as this chain, he's saying the groups are the same and the maps between those groups are the same. Okay. And I'm pretty sure that you also get the reverse inclusion, but I'm less sure about that. I'm pretty sure, but less sure, right? The statement in black I know completely is true, but the reverse direction, I'm not sure if there exists two spaces, which maybe under some mild conditions, like both are connected or something like this, then this reverse condition is true. But no, they both have to have the same number of components because each zero has to be. I don't know. Anyway, so the logic here is that if they were homeomorphic or homotopic, then their chains, then their homology chains would be the same, right? But since we just proved that their homology chains are not the same, it can't be homeomorphic or homotopic.
I think you can make like a really pathological example, but I'm not totally sure. By like, so if you were able to define an S infinity, right? Somehow you would be pushing out the Z component off the chart basically. And this, it looks like the H star would be isomorphic to the homology of a single point. Right? So like you have to have some condition on there, right? For like the same reason that like weakly contractible exists.
Oh, there you go. Okay, yeah, I'll write that down because that's interesting. So a potential counterexample would be to compare H star of S infinity versus H star of a singleton. But yeah, that would require being able to define an S infinity in the correct way. And that's why this is a potential counterexample instead of an actual counterexample.
Yeah,
because this space might not exist.
It might not exist. It's just that I remember when I was trying to clarify for myself, like, because Wikipedia has like a sort of circular thing when you try and look up what contractible means. Because like contractible could mean either that it's literally basically the same thing as a point, or it could mean that just pi1 is trivial. And those are two different statements, right? But then there's also another condition like weakly contractible, which is if all the homotopy groups are trivial, I think, which doesn't actually necessarily mean what you'd think it means, I think.
Yeah. So like one of the things that I know is that homology is an invariant. So in most invariants, the strongest that you can get for invariant is that if two spaces are equivalent, then the invariants are the same, right? Normally you don't get safe, the invariants are the same, the two original spaces are the same. So I'm now less convinced that this is true in general, that there might be some other examples which are maybe harder, but possible. So yeah, but that's the order of is, can I fit these all on one screen before we end for the day? The OneNote program is terrible. Okay, fine. This is as good as I'm gonna get. Great. Is that any two spaces which are homeomorphic are also homotopic, and any two spaces which are homotopic have the same homology chains. And so the other way to think about that is to just take the contrapositives of those two statements, right? If two spaces have different homology chains, then they're not homotopic, and if two spaces are not homotopic, then they're not homeomorphic. Right?
The way that I like to think of it is homeomorphisms are just really strong homotopies. Right?
Yeah.
They're homotopies.
Yeah, they're the homotopies where you don't need these brackets.
Yeah. So like if it's not even homotopic, well, homeomorphisms are a homotopy. So
and if it's just the homotopy that you need to take is just the identity homotopy, and you don't change anything, your time coordinate changes. Okay, cool. Well, that was our meeting for Tuesday. So I can write like another mock qual after I'm done with my oral and post that for next week if doing this mock qual was useful. I know that we didn't do that much of this today, partly because I'm scrambling studying for my oral exam, but I actually think that it's quite nice hearing from you all and then giving you all the practice to do some problems. So maybe for future mock quals, I'll post like a sign up and you all can sign up for like a problem each or something. And then, because there's 5 of you here today, and there have been pretty consistently 5 people attending. And based on the YouTube watches, there's been like 1 person watching the videos afterwards. So yeah, like 1 or 2 people. So maybe what we can do is that like everyone can sign up to like present a problem, and there'll be like 1 or 2 problems left over that I'll be stuck presenting. And then this way everybody like gets the chance to like work and present on a problem, and maybe people can like challenge themselves and like sign up for a problem that they don't know how to do as an excuse to like do some problems that they don't already know how to do. And this way, like we get to go through a lot of problems, and I'm not trying to write solutions for 9 problems every week or 2 weeks or something like this.
I have one quick question before
Yeah, sure.
we're done. So in problem 6, that formula, was that formula something that we were supposed to be able to derive on our own because of this class, or was this just always going to
This
be?
problem 6 was directly copied from an old qual.
Okay.
So in fact, with the exception of part 3, where I took 1 problem from my old final, 1 problem from your final, and 1 problem from an old qual, all of the part 2 and part 1, all of these problems are old qual problems. So,
Okay. So that formula can be taken as from God.
Yes, that question 6 was written exactly as it was written in the original qual question. So that means that really short solution that Raoul wrote was all that Schultz was expecting for this problem, because he gave you the hard part. Right, just compute the homologies and be like, hey, they're different here, and then you're done. Yeah, so the hard part of part 2 was question 5, but that's because I took question 5 from a non-Schultz qual. So question 4 and question 6 were both Schultz qual problems. So yeah, okay, cool. So I probably won't post the second mock qual till sometime late in the day Thursday. I'm going to spend the rest of my day today and tomorrow stressing about my oral exam. And then after my oral exam, I'll get back to doing stuff for this. So I'll
Good
try to
luck.
post.
You're gonna do
Yeah.
great. You're gonna do great. Yay!
I hope so. Yeah, so I'll try to post a second mock qual sometime late Thursday, and maybe I'll also post a sign up sheet and everyone can sign up for like the problem. And I think that could be a good way to continue on here. So, all right, thanks everyone for being here, and I'll see you all next, I guess Friday if you want to come to office hours, or Tuesday.
Yeah, will you still be there on Friday? Will you feel up for that?
Yeah, I'll be done with my oral by then. So
You're like, I'm gonna go.
either I'll be spending that office hour happily helping you all, or I'll be on the job market. So we'll see.
Awesome. Well, good luck.
All right, cool. All right, see you later, everybody.
Thank you.
Thank you.
Yeah, you're welcome.